So while I'm getting this set up, anybody have any questions about where we're headed? Due dates that are coming up?
The review covers like everything. Well, most of what's going to be on the test, right?
The review?
Yeah. Well,
You mean the thing I put on Canvas?
Yeah.
Yeah, so there's a lot of stuff there. Like I just like the last one, I don't expect you to work out everything on there, but pick and choose the things you need to review. But that should be a pretty good representative thing here. I think the quiz right now, the due date on Canvas is Sunday. I'm gonna move that to the following Sunday. So I realize I don't want, I'm not gonna grade them. I'm not gonna grade them this coming Sunday. So I might as well just tell you, you can take them over weekend. I put a deadline for section 3.7, which I think is
the Tuesday.
yeah. Okay.
Isn't there web work due tonight?
No. I didn't say on Canvas.
There was web work. Yeah.
It would be 3.5. That was due last time.
Yeah. Oh, okay. So if it's not set on Canvas, it's not due tonight, because there is one on web work that says it is due tonight.
No, yeah, he always changes that.
Right.
So the one that's tonight is next Tuesday, or 2 Tuesdays from now.
Okay, well, I'll change it on WebWork. Thanks for the heads up,
All right.
because WebWork will close tonight though. Without a change. Okay, thanks for the heads up. I'll leave myself a mental note to do that. All right. So we had to stop this example midstream. So where do we go from here?
Use L'Hopital's rule again.
Right, did we verify we could do that?
Yeah. It's really good.
So we still have a 0 over 0 form. So I can indeed do another iteration of L'Hopital's rule. So that's going to be the limit as x approaches 0 from the right of what new thing?
Was it e to the negative x minus 1 over?
Well, so this is where we ended up last time, right? And we can't evaluate this limit. So we're going to take derivatives again, right?
Right.
So what is our new numerator going to be? So the derivative of any exponential function will contain whatever the exponential function is, right?
Yeah.
But then I have to multiply that by the derivative of whatever the exponent is. What's the derivative of the exponent? Right, so that derivative is negative e to the negative x. Derivative of negative 1 is 0. Oh no. Not much better, good enough. So now we have to deal with the rest of it, right? We just said the derivative of e to the negative x was negative e to the negative x. So this first two terms in the denominator becomes positive e to the negative x. And then we have to do a product rule on the rest of it, right? So plus e to the negative x minus x e to the negative x. And I'll pause there because I went through that pretty quickly. So take a second if you need to convince yourself that that derivative is okay, or tell me it's not okay because I'm not.
This is product rule of the two parentheses.
This is product rule on x e to the negative x. Looking through it again, I feel okay about it. Yeah, okay. All right, so how do we feel about this limit now?
Well, the top, can't do it again.
Can't do what again?
It's also,
Why not?
because the top is gonna, come to the one negative 1.
So yeah, the top comes to the negative 1. So we're not looking at it. So yeah, there's no indeterminate form where it's negative 1 divided by something. We're gonna get a result this time. So the numerator is negative 1. And the denominator is what? 1 plus 1. What happens to x e to the negative x?
That's just 0.
That goes to 0. So all told,
-1.
-1/2 is the limit. A very long way to get there, but I don't really see. I don't see a more effective way to do it. So just to recap, I didn't do L'Hopital's rule first, right? Why didn't I?
You had to confirm it was a possibility.
You have to first get it to a type of indefinite.
Yeah,
form.
so I have to get it into a like this cohesive function divided by function.
Because it started as a minus.
Right, so yeah, it starts off as this addition of two. I don't want to call them rational functions of these two different functions. So really have to add them together and find a common denominator to do that. But yeah, so we verified 2 different times that L'Hopital's rule was something available to us. What we got there? Any questions on this guy? All right, so talk a lot about indeterminate forms. Some of those indeterminate forms are in the form of powers. So 3 cases arise from this. So if I have some limit of some function f raised to some function g, what's going to be a problem here? So if I raise 0 to a power, 0 raised to any power is what? Is that true for anything I could raise 0 to? That's something that people don't agree on.
Oh, anything to the power of 0, 1.
So anything to the power of 0 is 1, right? But 0 to the power of anything is 0. So something has to give when you have some kind of limit that has the form 0 to the 0. This is one of those forms that people don't agree on. Because we have those two, contradictory, rules that we all. The 0 raised to any number that makes sense is 0, and any number raised to 0, as long as that base makes sense, is 1. So what's going on here? In the case of those limits, got to do a little more work. What if the base is 1? 1 raised to anything is what? 1. But what if you're dealing with things where the power gets really, really large? And kind of the most important example we've talked about is this thing. This is one of those weird limits where the thing inside the bracket goes to 0 to 1, and the power gets arbitrarily large. What's the limit of that thing I just wrote down? It's not 1. It's e. That's where e comes from, right? So that's really, really not obvious, the fact that some number between 2 and 3 comes out of that. So it's one of the cases where we've got to look at a little deeper. Now, if the base gets really, really large, what does it seem like should happen if you raise that to some power? It should just always get larger, right? But we already told me that anything raised to the power of 0 is 1, right? So there's some kind of a conflict here. So, and again, we call these indeterminate forms because we don't have agreed upon results for what these are. Especially with the things dealing with infinity, which infinity is not even a number, it's really hard to get your hands on what that result is. So any questions about these 3 things and why they are problematic? Okay, so before I go on, I am not claiming that L'Hopital's rule directly handles any of this, but we have tools that can deal with them. So the limit is the x that goes to 0 of the x to the x. Is that one of the indeterminate forms we just talked about? What's happening to the base?
It's getting raised to itself.
Right, so what I mean by that is, what is the base going to, as I look at this limit? It is,
1 to 0.
so the base is going to 0 and the exponent is,
0.
so you could say, is that going towards 0 or 1? Maybe neither one. So we have an indeterminate form of 0, 0, right? So let's do this. Let's give this thing a name. Y equals the limit as x approaches 0 from the right of x to the x. So I can't use L'Hopital's rule here because I don't have a fraction to deal with. But what I can do is this, just like for, dealing with certain kinds of nasty looking derivatives, we can do this. I can take a natural log of both sides here. So the natural log of y is equal to the natural log of this limit. Because the function I'm taking that limit of is continuous everywhere it's defined, I can rewrite this in a very helpful way. The natural log of y is equal to the limit as x approaches 0 from the right of the natural log of x to the x. So I'll ask you this. Maybe you see that it's okay for me to do that natural log business, but why should I have done that? I had a reason.
Move the natural log allow you to remove the base, so you only deal with the power.
Not remove the base.
No, it would make it x natural log x.
Right, so I think what you're thinking of, Jezreel, is when you have the base of the log and the base of the argument, the quantity you're taking the log of, when they're the same, you get that canceling effect.
Right.
In this case, you don't have that because the base is variable, but what I can do is rewrite it the way that Jarek suggested. So in general, it's tough to deal with. It's tough to deal with situations where the exponent contains the variable. Natural logs give us a way to get away from it. Can I use log? So I'm not worried about this. So eventually I want to find a log. We're kind of skirting around that by doing this natural log of y. So now I have this thing. This is going to go to 0, right? This is going to go towards negative infinity, which is still indeterminate. Can I use L'Hopital's rule?
Yes.
How so?
Well, you would have to first, I think, multiply. Actually, I don't know. I was gonna say use the reciprocal of one of them to make a division, but I don't know if that works.
That absolutely works.
Okay.
So, right, I don't have a fraction here, right? Which means L'Hopital's rule is not something I can mess around with. But there is nothing saying I can't rewrite this function as, I'm going to choose to make x into its own reciprocal. I can call this the natural log of x over 1 over x. Do we agree that's the same thing as what the line above it says? Does this thing work with L'Hopital's rule? Let's make sure.
Oh, yeah.
As x goes to 0, what happens to the natural log of x? And it's a good thing it's 0 from the right, because natural log of negative numbers isn't even defined. So as x gets closer and closer to 0, what happens to the natural log? It doesn't go towards 0. It gets arbitrarily small. It goes towards negative infinity. What happens to 1 over x as x goes towards 0? I'm dividing 1 by things that are very, very small. Goes to positive infinity. So I have this thing. This, and this is an indeterminate form. I don't know what this is. So, and I think that's something I maybe haven't talked about until now, but when you're looking for infinities, doesn't matter if they're positive or negative. So this is totally fine to use L'Hopital's rule with. So I can say this now. The natural log of y is equal to the limit as x approaches 0 from the right of, and I'll make it clear that I'm invoking this guy, of, what's the derivative of natural log of x? 1 over x. What's the derivative of 1 over x? No, that's the square root of x.
Gonna be, 0 over 1.
When all else fails,
Oh, no, you have to do,
go to power rule on this one and just get it into a form where power rule is easier to apply. So what's the derivative of x to the negative first?
-1.
Negative 1
X.
to the negative 2, which I'll rewrite as -1 over x squared. So before I go any further, let's simplify. If I multiply top and bottom by x squared, I get negative x, right? Numerator turns into x, denominator turns into -1. So I get the natural log of y is equal to what? What's that limit there? 0. Okay, so we're almost there, but remember we took a detour. We haven't been looking at the limit we actually want to find. But I know that the natural log of the limit I really want to find is 0. So, and that's why we gave it a name, just so it's easier to keep track of it. So if natural log of y is equal to 0, what is y?
that be e to the 0.
E to the 0. So another algebra tool that I don't know if we've talked about a lot, but I can raise e to the power of one side as long as I do it to the other. What is e to the natural log of y?
That's 1. Or it's just y.
It's y equals 1. So the limit. So this is one of those cases where, and here's the temptation I want to try to steer us away from. It's that, oh, so 0 raised to the power of 0 is 1. No, we don't know. In this particular case, that where the limiting form is 0 to 0, 0 to the power of 0, you get that. But I'm sure there are examples where we can make this limit anything else. Any questions on how we dealt with that? Okay. What about this thing? So in this case, we have what's happening to the inside of the parentheses as x gets really large.
It's getting small.
The inside gets one.
Yeah.
Getting smaller, going like trending towards what? Does it have a limit?
Oh, 21.
Towards 1. And the exponent's going towards infinity, right? So this is another one of the forms we talked about. So impossible to evaluate directly, but let's give it a name again. All right. So what did we do last time to start making this a little easier to digest?
So this time we took the natural log.
So the natural log, would that be useful here? Let's ask ourselves, why was it useful in the last case?
Because it was exponent raised to the power of said exponent.
Right, so you had the variable in the exponent, right? I have that same situation here. So I believe that that's at least considering for this one again. Natural log of y equals the limit as x approaches infinity of the natural log of 1 plus 7 over x to the x, which we can rewrite as x times the natural log of 1 plus 7 over x. Is L'Hopital's rule available to me here? Don't really have a fraction. So is there a way to rewrite this to make L'Hopital's rule available?
X over 1 plus 7 over x. Or just the second time log over under 1.
You could do that, but then you have to take the derivative of 1 over the natural log of something, right? Which is totally doable, but I am going to suggest this instead. I believe that would be easier to deal with all this stuff.
First term is x and then make the denominator.
Yeah, so in general, multiplying by something is the same as dividing by 1 over something. As long as something isn't 0. All right, so does L'Hopital's rule help us here? Can it help us here?
Oh, maybe, we have to.
You gotta find that out, right? What's gonna happen to the, well, I'll solve the denominator first, I think it's probably clear. As x goes to infinity, what's gonna happen to 1 over x?
It's smaller.
Does it have a limit? It's not gonna be negative infinity.
Isn't it gonna go to 0?
That, the denominator goes to 0. What does the numerator go to? I don't believe it's going to 1. So let's break it down. Go ahead.
I'm just gonna say 0.
It goes to 0. So let's break it down. 7 over x. What's 7 over x going to do as x gets large? Towards what? 0. So then you have the natural log of 1 plus 0. What's the natural log of 1?
0.
0. So this is good for L'Hopital's rule. I'm trending towards 0 over 0. So now I can say the natural log of y is equal to this new limit. You tell me what the new function is that I can deal with here. Go ahead.
But you're allowed to split up the numerator into natural log of 1 plus the 0.
Yeah, that's all those are defined. It's all defined.
This is 1, okay.
Yeah, I mean, so the limits that I dealt with kind of on that process were, 0, 1, and then 0. So as long as all the links in the chain have definite limits, have real limits, it's fine to break them down later. All right, so I'm going to fill in the denominator because we just dealt with that derivative. Negative 1 over x squared. The derivative of natural log of 1 plus 7 over x. What's the derivative of natural log of something?
1 over.
1 over that thing, right? So 1 over 1 plus 7 over x. And then I have to multiply it by the derivative of 7 over x, right?
Mhm.
So that'll be minus 7 over x squared. How are we doing?
I just want to confirm that you get that same kind of form for every time you have a number over a variable, a negative number over the variable squared. Like
Yeah, so in general, yeah, this is always true, and this is a very special case of the power rule.
for any number is a numerator.
Oh yeah, I mean that one. So yeah, And that comes from another, that's because basically 7 over x is a constant multiple of 1 over x, right?
Right.
So the derivative is going to be 7 times the derivative of 1 over x.
Yeah, I just want to make sure.
Yeah, those things always apply in general. Go ahead.
And the inner function is -7 over x squared. For
The derivative of the inner
the
function.
derivative, yeah.
One convenient little canceling thing I get is the signs. We'll go back to positive. X squared, x squared. So now I get natural log of y equals the limit as x approaches infinity of 7 over 1 plus 7 over x. What do we do with that?
Do you have to evaluate for use of L'Hopital's rule again?
Let's see.
Oh, yeah, so 7 on top.
So that's hard to know, right?
Yep.
So L'Hopital's rule's out, but maybe we don't care.
Maybe we just there.
Is the limit, can we think about what happens as x is really large and just evaluate the limit?
Yeah, so it'd be, the limit is 7.
Because what happens in the denominator?
The denominator, 7 over x goes to 0 plus 1.
Right, so the denominator goes to 1, so taking x to infinity gives us natural log of y is equal to 7. So what's the limit then? The very original limit we asked about at
Is,
first.
y equals e to the 7.
Right, so if we exponentiate both sides. And one thing I want to remind you, I just wrote in the last slide, but the definition of E that we've been using, one of them anyway, is this. Which looks very similar to the thing we just did, right?
Oh,
So make that, yeah, take that second term, by only multiply by 7, and we get e to the power of it. Any questions there? If not, I got one more indeterminate power case to show you. X to the power of 1 over x. So what happens to the base here as x goes to infinity? The base, the base grows without any bound, right? What happens to the exponent?
It shrinks, goes to 0.
It shrinks, yeah, it starts, yeah, it trends towards 0. So you have this form, which this is, yeah, not something we can agree on, so we need to do some work with it. So y equals this limit. And did I already say or ask, like, why am I bringing in this y thing? Is it clear why I'm doing that?
yeah, just to make it easier.
Make what easier?
Adding natural log on both sides.
Okay, yeah, so, yeah, because really 95% of the work we just did in the last 2 examples and what we're about to do are not really directly involved with the limit where I'm actually wanting to find. So just giving it a handle.
Defining it as a y.
Yeah. So y equals this limit. All right, what can I do from here?
Natural log of both sides.
Yep, so the natural log of y is equal to this limit. This will jump to the natural log. All right, now what?
So that becomes 1 over x, natural log of x.
Yeah. All right,
That's just natural log x over x.
indeed. So we got a fraction, which is, I mean, one part of the recipe for getting the L'Hopital's rule involved. What happens to our numerator and denominator? As x gets very large.
The numerator increases to that bound.
Okay, so that goes to infinity. What about the denominator?
Does the same.
Does the same thing. So we're good. So this goes to infinity over infinity, which means y is equal to this new thing. The limit. Oh, not y, natural log of y. Is equal to the limit as x approaches infinity of what?
1/x/1.
Yep. So natural log of y is equal to the limit as x approaches infinity of 1/x, which is what? What's going to happen to 1/x as x gets really large?
Zero.
Goes towards 0. So got natural log of y equals 0, which means y itself is no,
E to 0.
e to the 0, which is 1. Seemed like we didn't trust our instincts on that. Any questions here? All right, I believe that's all I have. Anybody have any questions about anything at all? All right, have a good break. I will see you. Yeah, see you next Monday.